going to learn how to efficiently raise complex numbers to powers. We know that you could take a number like this, 4 minus I, and raise it to the 5th power by just multiplying 4 minus I by 4 minus I times 4 minus I. Keep multiplying. And you could multiply these two and get your result, and then multiply in the next one, and the next one, and the next one. And that's definitely doable. But it is a little bit cumbersome and would take a little bit of time. And then as another possibility, you could use the binomial theorem to raise 4 minus I to the 5th power. But I don't want to talk about either one of those strategies. I want to talk about the efficient way to raise a complex number to the power, and that is using DeMoivre's theorem. So let's talk about what that would look like. Suppose I have z equals, and that's our complex number, equals r times cosine theta plus I sine theta. In other words, we're going to write the trig form or polar form of the complex number. Now, if we wanted to raise z to the 2nd power, we know we would have r times cosine theta plus I sine theta times r cosine theta plus I sine theta. But we know how to multiply complex numbers together in trig form. We multiply the magnitudes together, so r times r is r squared, and we add the angles. Theta plus theta is 2 theta, so we would have cosine 2 theta plus I sine 2 theta. And we have just raised this complex number to the 2nd power. Suppose we wanted to raise it to the 3rd power. Well, we know that that would be z squared times z, so I could write this as r squared cosine 2 theta plus I sine 2 theta times z, which is r cosine theta plus I sine theta. And again, I multiply these magnitudes together, so r squared times r is r cubed. And our angles, we have 2 theta plus 1 theta, that's 3 theta, so we have cosine 3 theta plus I sine 3 theta. And notice what we have. When we were raising this complex number to the 3rd power, we would raise the magnitude to the 3rd power and multiply the argument or the angle by 3. And in fact, this is going to be true in general in DeMoivre's theorem. Here's what DeMoivre's theorem says. It says that if you have a complex number, and of course written in trig form or polar form, and we are raising it to a positive integer power, we can raise the magnitude to that power and multiply the argument by n. So let's see that in action. So the directions will be, for the next problems, they'll be find the power of the complex number, and we're going to write the result in rectangular form or standard form, a plus bi. And here's the one we'll do first. Notice our complex number is already in trig form. So away we go using our DeMoivre's theorem. We raise 5 to the 3rd power, and we multiply the angles by 3. So we have cosine of 3 times 80 degrees plus I sine 3 times 80 degrees. And let's do some simplifying. So we have 125 times the cosine of 240 degrees plus I sine 240 degrees. And if we were asked for the answer in trig form, we would be done. We have just raised this number to the 3rd power. But these directions ask us to write it in standard form, this a plus bi form. So let's continue. We're going to simplify this by substituting in its value. Let's see, the excuse me, cosine of 240 degrees We're in the third quadrant, so we would have -1/2. Also in the third quadrant for the sign, we know the sign is negative there as well, and its value is square root of 3/2. And we can distribute that 125. So we have -125/2 minus 125 square root of 3/2i. And we now have this complex number raised to the third power. Let's do another one. Here's the number. We're going to raise the complex number negative square root of 3 plus I to the 6th power. Now, to use DeMoivre's theorem so that we can do this efficiently, we need to write this number in trig form. So let's do that. I'm going to draw myself a little picture over here to help me think through the process. So let's see, we would go negative square root of 3 in this direction. And again, I'm considering us on the complex plane. So here's our real axis and our imaginary axis. And then we would come up 1 in this direction. And hopefully you recognize that triangle there. We have a 30-60 right triangle. So this magnitude right here would be 2. And this is a 30-degree angle or a pi/6 angle. Let's work in radians this time. So it makes this angle right here 5 pi/6. So our complex number in trig form would be 2 times cosine 5 pi/6 plus I sine 5 pi/6. There's our complex number, and we're raising it to the 6th power. So DeMoivre's theorem says we're going to raise 2 to the 6th power. Well, we can do that. 2 to the 6th would give us 64. And we multiply 5 pi/6 by 6. Well, that's kind of nice. We have cosine 5 pi plus I sine, whoops, I lost the I sine 5 pi. Well, we know that 5 pi is coterminal with pi, so let's just rewrite it this way. Cosine pi plus I sine pi. And again, if the directions said to stop in trig form, I would present that as my answer. But the directions say to go to rectangular form, or this a plus bi form. So let's substitute in our values. So the cosine of pi we know is -1. The sine of pi we know is 0. So if we multiply these together, well, 64 times -1 is -64. 64 times 0i is 0i, but we don't need to write that part. So what we've determined is this complex number raised to the 6th power is -64. Let's do one more example. We're going to raise 4 minus I to the 5th power. Now, again, we're going to change to trig form. So let's figure out what this complex number is in trig form. I'm going to draw it right here again. Let's see, 4 minus I. That means I would go 4 in this direction and -1 in this direction. Right? In other words, this point right here represents the number 4 minus I. And we can use our Pythagorean theorem and determine that this length here is 17. Or how about we make it a square root of 17, right? And now we need to figure out how big this angle is right here. If you use your calculator, and I'm going to work in radian mode. Right? If you take the inverse tangent of 1/4 or negative 1/4 to figure out how big this angle is. I'll just do that right now. I'm going to use radians, so make sure your calculator's in radians. If you do the inverse tangent of negative 1/4, you'll find that you get negative 0.2449. And a negative angle, I just want to put the angle between 0 and 2 pi, so I'm just going to add 2 pi to that. So I get this angle is 6.0382. And I gave quite a few places because I would like my answer to be pretty accurate. So I have this square root of 17 times cosine of 6.0382 plus I sine 6.0382. And we're raising this to the 5th power. So let's continue. I'm going to just come over here a little bit so that I have room. And don't, right on top of this. We raise square root of 17 to the 5th power. And remember, square root of 17 to the 5th power would be square root of 17 times square root of 17 times square root of 17. Right? So we would have this 17 times this 17 times that square root of 17. So we would have 289 square root of 17 times cosine, and I'm multiplying by 5. So multiply this angle by 5 and you would get 30.191. 30.191 plus I sine 30.191. Remember, these are in radians. This was in radians, so this is also in radians. Now, when I'm doing this problem, I actually have on my calculator not just this number right here. When I multiplied by 5, I actually have, I actually have 30.19103322 on my calculator. I'm going to leave all those places in my calculator so that my answer will be more accurate. I wrote this down this way, so it's easier for me to follow what's happening. And if I were going to present my answer in trig form, I could leave it here, or maybe I would find a coterminal angle to this that's between 0 and 2 pi. But since we're going to rectangular form, there really isn't any need to do that. I'm simply going to distribute the 289 square root of 17 to this value and distribute 289 square root of 17 to this value. Now I want to show you the result two different ways. Suppose you just cleared out your calculator and you just used it as written. You would get an answer that looks like this. 289 square root of 17 times this number is 403.96. Distribute this number to the I sine 30.191 and you would get minus 1121.01 I, which is pretty darn close to the exact value for this. Now, when I did it, I left this on my calculator with more decimal places. So when I did that and pushed cosine of that number to more decimal places, my calculator gave me this value, 404. Notice very close to that. Similarly, when you use the number here to more decimal places, you end up with negative 1121. Again, very close to that, I. And if you multiply 4 minus I to the 5th power out, just in rectangular form, as I mentioned at the very beginning of this lesson, you'll find that it is exactly equal to this value.